Comments. Here is this giant mass of papers that went around already one time. If you have picked up your stuff, then it's not in there, and that's good. This is stuff that has already gone around one time, and it's just been accumulating there in the lab. And I thought I would just take today to say, okay, I'm going to just throw that around there, and if you find anything that's yours, take it. If you don't want to find anything that's yours, that's fine. The stack will just get bigger, and eventually in the middle of summer sometime I'll recycle everything. But anyways, there's the homework. I still am obviously very behind on getting the things back to you, so that's still coming. I got a lot to get back to you on that. I will do that. I wanted to point this out, that the nomination forms I gave everybody for faculty lecturer, if you've some have given me back to that, others of you haven't. If you're still working on it, that's fine. Just wanted to encourage you and remind you to do that. Also, then I wanted to look a little bit at the calendar. Like I said, we're way behind. I really want to get started with the next chapter, but I feel like I need to do at least a little bit more, but not enough, really, of this last chapter, 36, before we put closure to it. So I'm going to take a few important discussions about 36, and then we better move on into 38, and then 37, and then 38. And we'll probably have to truncate a little bit of that last chapter, 38, unfortunately, but I don't want to put off our next unit any further than one day. And I say one day because I'm looking forward going, okay, if we take this week and next week to lecture, then we can follow that on the test the next Tuesday. And so if you're looking at your syllabus there, our optics test is scheduled, let me just get the date right here, for a Thursday, April 25. And my thoughts are, since we are way behind, that if we truncate and push back one day, that makes it on April 30th. And then that gives us 2 weeks to do. So that's kind of what I'm leaning towards, but I'd like some feedback from you. And so I say that now. Pushback's not a good idea? Is that what you're shaking your head? No? No. It's not because of test?
After our math test.
It's the same day as my
Oh,
math
you
test.
we had the last one on the same.
And and at some point we'll probably end up taking a vote. At this point, I'd just like some feedback from you guys on what it is, because what I really don't want to happen is to make things worse instead of better. But in this case, we really are really far behind, and I'm trying to squeeze that one in on a timely manner. I don't even know if that's even a possible option anymore, to be quite honest. Oh, and then go to Thursday the 2nd. Well, that's something to think about too. And then we could start the next unit. Would you guys even listen to me on the next unit, though? If we have no.
It would give us time to answer and ask questions on the homework you've done.
That that is a lot good said about that. All right.
All the 220 tests are on Monday.
And Monday, Tuesday, and then you guys would be on Thursday. Yeah, I'm liking the sound of that. Let's keep talking about that and then continue this discussion. So, yeah, that would give us time. That'd give us a chance to start the next unit, and it wouldn't put it right next to your math test. Okay, good. All right, now with all that said, let me just kind of do at least the grand finale. And so maybe I spent too much time drawing those triangles at the beginning. I think that's where I made a mistake here on spending too much time. But I think it really led the foundation of this equation. And what I wanted to emphasize this morning here is this equation. We finally got through it in terms of both the mirrors and the lenses. And so whether you have a flat mirror, or the concave mirror and the three options it has, or the convex mirror and the only option it has, or whether you have a flat piece of glass, or whether you have a convex lens with its three options, or the concave lens with its option. Those were the 10 I was talking about. This equation would work for all 10 of those, as long as we're willing to pay close attention to the signs, whether we use positives or negatives. And simply put then, P can be positive or negative. Now, it can only be negative, and I think that's the hardest one of all, if it is a virtual object, which can only occur if you have a lens system or mirror system, optical system, I guess I should say, where the image from the first one becoming the object for the second one, the second lens or mirror is placed before the image is created. So that's the hardest one of all, I think, to understand of when that one is negative. These other two, I think, are a little more straightforward. The Q is positive when the image is formed where the light really goes. And so if it's a mirror, it would bounce back in front of the mirror. If it's a lens, it would transfer through and go on the other side of the lens. And so we call that the real side. Where if it's on the other side, where the light is not really, which would be behind the mirror or in front of the lens, then Q is negative. And then F could also be positive or negative. And for the concave mirror, trying to get those straight, it was a positive, and for the convex mirror it was a negative. All I did last time was show you the different situations that you can have a positive and a negative lens. I showed you a lens that looked like this, and I showed you a lens that looked like this. And in this one, this made the light converge to a focal point. And this one made the light diverge. And so, like the convex mirror, the concave lens, we treat as a negative focal length. And unfortunately, I didn't have time to make the big step I wanted to make is then what determines the focal length of a lens. For a mirror, this was pretty easy. For the mirror, the focal length was half the radius of curvature. But for the lens, we argued that the focal length would have to do with the curvature of each side of the lens, as well as the index of the material that it's in. And so that's kind of the big last step, and then some little things here to wrap it up. Let's take a look at this picture. Your author does a good job. Let me go through it, maybe a little quick here. I'll use your author's diagrams and save a little time for me drawing them. Hopefully that won't be too quick, so you'll be able to take some good notes, but they are in your book here. Let's do this. Here's what your author says. If you want to understand the operation of a lens, if you want to know whether the focal length is going to be positive, converging, or negative, diverging, then what you need to look at is you need to look at the two surfaces plus the index of the material. So of course, let's do this one surface at a time. So your author says, look at this first surface. What would happen if you had this? What if you had some object here, a distance p? From the surface. What will happen is the light will begin to spread out. If it goes from index n1 into n2, where in this case n2 is greater than n1, but not every case is that going to be true. But in this case it is. What that will do is bend the light towards the normal. Now, in this case they got the light bending so much that the light that is spreading out then begins to converge. And so this light would converge, and so if this was a giant piece of index N2, say it's glass, then an image would be formed this far away. And so there's our pictorial view of what the light would do. I would say it would form an image even if it did not make it come down to a point on this side. It could have just not made the light converge, but just make it diverge less. And so it would bend it and make the light look like it was coming from back here. So that could have happened too. And you'll see here the math works out the same, whether the image gets formed on this side, so real image, or whether the image gets formed on this side, virtual image. But the real key is to say, let's just look at one surface at a time. And so just like I was trying to argue for you last time and want to emphasize, when you have a harder problem, and this is one example I want to do, if you have an object and then a lens and a second lens, you have to first calculate where is the image formed by the first one, and then the image from the first one becomes the object for the second one. And that's exactly what we're going to do here. Let's just do the next step here. Let's go through some math and some geometry here. Your author views it this way, and he says, let's take this. Here's our surface. We take an object that's over here at a distance of p. The light comes out. Let's just look at one beam at some angle alpha. It then hits the lens right here at some height d. It then bends and then converges right here. So of that last picture I have, this is just one of those mini beams with a bunch of triangles and other information that will allow us to get an equation here. So going through this geometry, I would say, okay, this distance is p. This is the object. This is the image distance. The surface is curved, and the radius of curvature would be back here, where he calls this the point C. And then he draws a line out to that intersecting point where the light intersects the surface, and he said that would be the normal. And so applying Snell's law, you see that you have theta 1 coming in, it bends towards the number and now becomes theta 2. And so I'll put that on the board. That would say n1 sine theta 1 is equal to n2 sine theta 2. Oh, that would be my first math. That's the physics of what happens to the light as it bends. Now, let's put some other relationships up here real quick. I'll start with this for a second. If you look closely at a very big triangle right here, and we go back to a little geometry, so maybe I will right here do a little geometry. If I have a triangle, any triangle, and I have my three angles, alpha, beta, gamma, I think you already know, what do those three add up to? 180, fair enough. But let's do this. Let's draw an extension of one of the legs. Let's call that an exterior angle to the triangle. Let's call that one delta. So we've got alpha, beta, gamma, delta. What would you say about delta and beta? And they add to 180 also. So alpha and gamma add up to delta. Does that make sense? Right? Try it again here, right? These three add up to 180, and these two add up to 180. So delta and beta add up to 180, and alpha, beta, and gamma add up to 180. And so when you take all the beta away from each side, you of course get it. You probably remember this, or I'll re-remind you of it from your geometry class, that you learned it as this way. The exterior angle to a triangle adds, or is equal to, the sum of the two interior angles, or the two opposite interior angles, I think is how they describe it. Here's why I say that. Take a close look at what this picture calls alpha and beta. See this big triangle? Isn't theta 1 an exterior angle to alpha and beta? So I would say that theta 1 is alpha plus beta. Okay? Now, let's also take another triangle. Same geometry. This triangle would be from P across the ray down to the image, back to the center of curvature, along the radius, or normal here. And I'm going to look at that triangle. Because that triangle has two interior angles. It's a theta 1 and a gamma. Oh, by the way, I hope, maybe I shouldn't have used Greek letters here. I don't, because, you know, okay, now that I'm done with this, I don't want you to think that the alpha and the beta and the gamma here are the same as over there. So forget about those. This is my alpha, this is my beta, this is my gamma. Okay? But I am saying that these two angles need to add up to beta. All right? Fair enough? So, Snell's law, geometry. Now let's do some trigonometry. Let's look at the tangent of, and I guess I will first put alpha. The tangent of alpha is what? Yeah, it would be a d for the vertical and over p. So d over p. Now again, roughly, you may argue that p is a little bit smaller than the whole length of this triangle because of the curvature. Fair enough. But in a second, we're going to also argue that we're going to talk about small angles. And that small angles of incidence will occur when either this curvature is not much, so this is back to here, or that this ray is down real low and going right there. And so really the only images that get formed are from the light that goes through a small part of the lens. And this part of the lens is actually, unfortunately, making it blurry. And so it would be nice to block that part of the lens. Okay. I'll do the tangent of the other angles too. Tangent of. But if you look at the tangent of beta, what do you have? Well, beta would be a d over roughly an r. And so again, a rough approximation, not exactly. We talked about that before, so I'm going to go with it. Gamma, same thing. Tangent of gamma is a d over a q. Let me also be quick to point out that as I'm doing my geometry, haven't I treated everything as positive numbers? All right, so again, like all of our optics, we got to make sure what do we mean by positive numbers. And so this working out, I think, helps me remember, and I'm hoping it helps you remember, what are my definitions of positives. And so, of course, my positive P is when I have a real object. My positive Q is when I have a real image. My positive R, this is kind of interesting, is what? When it is curved over here where the light goes. Right? Now that was a little different than we had for the mirror. Right? For the mirror, remember which one was positive when it was curved this way. And so that's a recipe for disaster if we're not paying close attention here. But I think again it helps to realize, well, that was a mirror and this is a lens. And we treated them opposites because the light goes back in front of the mirror. So again, when the center of curvature is at the location where the light goes, not where it comes from, but where it goes, R is positive. So if you look at this mirror, the light comes out this way and goes that way. The center of curvature is where the light goes, positive. Here, the center of curvature is where the light goes, right? It hits this surface and goes this way. Center of curvature is on this side. So, just want to make sure I pointed that out. I'm treating R now as a positive. Because what do you think I would do if the surface was curved the other way? Yeah, exactly. I'm going to treat R as a negative number. Okay? But this one, let me just kind of work it out with all positive numbers to get us started. Here's where our small angle approximation and a bunch of substitutes come into place here. Let's, for the sake of discussion, say that we're not going to have big angles. We keep everything under about 30 degrees. The sine of, what's 30 degrees in radians? Pi over 6. Okay, so pi over 6. But as long as we're willing to do pi over 6 or smaller, then, like I said, we've done this many times. Try your calculator. It'll work out fine. So I'm going to take an approximation there. And once I do that, it really makes our math easy. Because this becomes now N1 alpha plus beta. And this then becomes beta minus gamma. And as long as I'm taking a small angle of a sine, then these would have to be small angles. So this would really be approximately alpha, this would be approximately beta, and that would be approximately gamma. So this becomes N1, and in place of alpha, I could put a D over a P. In place of beta, I can put a D over an R. In place of beta, I can put a D over R. And in place of gamma, I can do a D over a Q. Fortunately, there's a D everywhere, and now I have what I wanted. The relationship between the image, the object, the radius of curvature, and the index that is making the light bend. Yeah?
So if you're just calculating for the position of an image, couldn't you always assume that the angles are infinitely small?
Infinitely small? You mean like 0 or?
Like really, really, really tiny. Because we have our D is pretty big right there, but you could do all the calculations just as easily with
D small?
D that was a tenth of that size, right?
Yes. Yes. And that's essentially what I am doing. So what I'm saying here is this math is pretty much only valid for the light that hits in this area. And the light that gets further out, it's less true. So if I were to put a screen right here and block all the light except in this area, I would get a nicely formed image according to that equation. But as I open up my aperture and the light hits further up here where those equations are less true, the image is not necessarily formed at this spot again. Now the image is formed a little bit forward of that. Backwards. It might be back. But a little bit off of this point. And therefore, when you open this up, what you would get is kind of a blurring effect, if you will, is you would get the image not quite as clear because the rays that are coming in this area form a nice image, but the ones that form here don't. And then when you move the screen back, now these rays form a nice, I think it's forward, form a nice image, but these rays then don't. So, as I said, it's more accurate the closer that is. That's why a good photographer will narrow in that aperture and say, just let it go right near the center of the lens. The downside of that is the intensity of the light.
Does a flat screen fix those problems? The ones that you showed us last time? If they have the curves so they're all flat? It looked like a jagged tube on the side.
It helps. But no, it doesn't fix it. Yeah, it's a little better. Yeah. And it actually introduces some other problems. So those are even actually can be worse as far as making clean images. But you know, the part where the weight, that was a Fresnel lens, but in terms of the weight, yeah, there's some huge advantages there. Yeah. But they introduce some interference effects, which is the next chapter. Yeah. Yeah. Well, I'll finish this up then by saying if I put the object and image together on one side of the equation, and then the two that are over the R on the other side of the equation, I have at least a start. I would not say I have a lens equation yet. In fact, I like to call this the half lens equation, because what have we done is only calculated where the image would be formed if you had just one refracting surface. And in fact, to give you some understanding, I thought I would bring one out here. Let's pretend we had something in the glass block. Now, we don't really have something in the glass block, but we can get a good approximation by putting something right at the bottom and holding it tight. And so I'll pass this around and give this a try. If you place it here and you place the glass block, what's nice is if you look down into the glass block versus off to the side of the glass block, what will you see? This is obviously straight through where the paper really is. But when you look at here, what you're going to see is the image. And I want you to see that the image that is formed because of the bending of the light does have a different appearance. I'll go through some numbers in just a second, but in this case, it looks like the writing is closer to me. You can clearly see that instead of being this far behind the block, it looks like it's only about this far behind the block. And you can see, like I said, really well, I think, how much closer it really looks to you. And then, of course, also it looks magnified here. And so I'll go ahead and do a first calculation here. In fact, that's the next little image in your book that hopefully you've got a chance to kind of do. This is what would happen in drawing the rays. You see the light is coming from some distance p. And in this case it would be the size of that glass block. I didn't look real closely at it, but I don't know how tall is that thing, about 4 centimeters or something. But if this is the letter O, then when the light comes out and it hits the air and it bends away from the normal, your eyes are going to perceive the light as coming from this point, Q, and Q then would be a shorter distance or a smaller number than P. In fact, let's even just put some numbers in here. I would put a 1.5 for where the light is starting, because it is starting in the glass block, and many of our glasses are 1.5 or well, it's hard to say that, they vary so much, but that glass block is what you guys used in lab, if I remember right, and I think you got numbers around 1.5 there. If I put this as a point P, and then I say it goes into the air, and so index number 2 is the air, and I ask myself what is the Q, then I can come over here and manipulate this one around. This would be 1 minus 1.5, although the numerator doesn't really matter, because what's this? It's a flat surface. So what's the radius? Yeah, so very large, right? So we'll go in infinity. So 1 over a very big number is 0. And so when I go to solve this, I get 1.5 over P equals 1 over Q, negative. Do the upside down theorem and you get a negative P over 1.5. And so as a quick example here, this is where my image would be. My image would be whatever P is, which like I said is probably around 4 centimeters, divide that by 1.5, and that then is where the image is. And that's what I wanted you to see. You would see an image. Notice it's negative, right? Negative. So it tells me it's a virtual image, which it tells me the light appears to be coming from inside the glass block, not elevated above the glass block. Okay. But it also tells me it is closer to the glass block, as this picture shows. In fact, I think your author has done a good job of then illustrating an example of this is not so much looking at this lettering, but somebody looking at a fish. And so they have somebody standing here looking at a fish, and again, the fish is a depth D in the water, but it will appear to be a depth Q in the water. It'll be closer up by, and then this is water, so the index is 1.3. The calculation would be similar, and you'd end up with a 1.3. So everything's going to look a little bit closer up. And you've probably noticed that if you've looked at fish, although sometimes it's hard to even know because you don't really know where the real position of the fish is. You just see the fish, and you're not really sure it's close. But if you ever reached in and tried to grab the fish, there's a good chance you'll notice right away that you went like this, thinking you were going to grab the fish, and you just missed it. The fish was a little bit deeper than that. You're like, oh, man. And so it's a lesson of optics that the baby bear, as I learned pretty quickly, or a baby bear doesn't become adult bear, and that kind of thing. So you got to know where that, like I said, that fish is. Maybe in your case, you notice it more in a swimming pool with the black lines. If you look down at the bottom of the pool, they got the lanes. You'll look at them, and the bottom looks closer. It looks magnified, and you even sometimes jump in thinking, oh, I'm going to touch the bottom, and oh wow, that was deeper than I thought it was going to be. Exactly. And then you look at the black lines underwater and you go, wow, look how far down they are. And you lift your head up and you go, yeah, see, look, they're close. Oh no, they're far. Oh no, they're close. Or maybe it's only me who does that. Just swim, get some exercise. But there's a difference in that, yeah.
What is and why is that avoided when you wear goggles?
Pardon me?
Is it avoided when you wear goggles, and why?
Okay, well, now let me backtrack to that a little bit with just the eye itself. Is if you'll notice, without goggles or mask, things aren't so clear underwater, are they? Why? Well, the light has to bend, yeah?
Because the lights, the eye is specifically adjusted for the change in index.
Okay. Oops. Oh. All right. Am I still on? Did I pull it out? All right. Yeah, I guess what I was looking for here is your eye does some bending right here on the surface, on the cornea. And as the light comes in, going from air to cornea, salt water, you know, mostly, there's a lot of bending that occurs right there. Now, there's more bending that occurs deep inside where you have the lens. Let me look at another picture here. But the fine adjustments, here's a kind of a model of the eye, is the light bends here, and then the light also bends here. But the amount of bending of light between the air and your cornea is how your eye is designed. As soon as you put your eye in water, now you have water going into water. There's very little to almost no bending going on there. If you remember back in 35, I had those spheres in the beaker and I poured the water. Do you remember that? And those spheres looked like they disappeared because there was no bending of the light. And so that's why it's going to be difficult to see without goggles on, because your eye, as you said, is designed for that interface between air and the cornea. So you need a little bit of air in front of the cornea for the bending of light. Doesn't matter how much. So little goggles or big face mask or a whole old-fashioned bell jar where you're in the whole thing, a bell tube there, and you know, as long as there is some air between there, you've got the bending correctly. Which wasn't quite your question, but I did want to point that out, that's, you know, why things will look so clear once you put on a mask or goggles and then your eyes work correctly. You asked, though, what was yours again?
When you wear the two-part goggles underwater, you can see fine. Like their depth perception is okay, right?
Yeah.
How is that different than when you're out of the water?
But now here brings up a question: is the I think the line still looks a little bigger, doesn't it? Now you make me wonder. I think it does. I think it still looks magnified. Now you're going to make me look.
He's like, I'll be back.
I think you still see it magnified. Now I don't know that. Now you're going to make me wonder. I think you do, though. Wow. I don't think it looks quite the same. I think when you take them off, they look far, and then they look magnified. Anybody know?
Yes. I don't think it does.
You think they look magnified too?
I think it's
Yeah, I think it still looks the same.
I think I remember like swimming and like trying to grab the ball.
Oh, and it's not there. Yeah. So it's something you learn that, hey, things look magnified with these goggles on. Yeah. Oh wait. Well, anyways, back to this. I again just wanted to point that out, because here's part two. Part two of this, to get to the lens, is to say, all right, now that I've bent the light on the first surface, let me also bend it on the second surface. And probably a good illustration is maybe this one here. Maybe I'll do this one here. Because now let's do this twice. And then we finally get to the result that I really wanted you to see here, is how are we going to figure out what the focal length of a lens is? Because it has to do this twice. And so I'll clean this up, but I'll work around this equation here. Actually, maybe I'll just put this equation over here. So index 1 P plus index 2 over Q equals the difference in the indices over the radius of curvature. And so if that's the equation for the object and image based upon one set of curvatures, if I have something that looks like this, and then something that looks like this, let me call this then surface number 1, and then let me call this surface number 2, or barrier number 2, or however you want to describe it. But this one here is going to have a radius of R1. This one here is going to have a radius of R2, which, by the way I've drawn it, that would really be a negative number, but I'm not going to worry too much about that at the moment. Let's just do our first calculations. Let's go ahead and say that we are in the air and we are going into some kind of medium n. If I apply this equation for the first surface right here, I would go 1 over p, and when I say p, I mean the object for the first surface, because that's going to form an image, and the image from the first surface is going to become the object for the second one. Okay? And so when I write this as n over q, it's q1. In other words, the image formed from the first surface equals then n minus 1 over r1. If I write that same equation for surface number 2, then we would be starting in this index going out back into air. So I would have n over p2. Now remember, p2 is the object for the second one, which of course is going to be the image for the first one here in just a second. And then if I go plus 1 over q2, then equals where it goes into, where it comes from, divided by radius number 2. And so, applying this twice, surface 1 and surface 2, and then looking carefully, isn't the image from this one the object for that one? And so if I had the light starting here, and then it would form an image here, not worrying about the second surface, this would be the image, right? What would P2 become? I'll start with the question, positive or negative number? Yeah, in my picture it's a negative. It would be this distance here, right? And so this distance would be this whole distance, which you might call Q, minus T, where T is the thickness of this lens.
What's the distance Q?
Huh?
From what point to what point is the distance Q?
Say it loud, I can't hear you.
What distance is Q? Because it's going to be different at different places.
What distance is Q? Q1 is the distance of the image formed from the first surface. Yeah, right. And what I want to say here is I would like to take this first one and solve for Q1. Because Q1 is now going to become P2. The image from the first one becomes the object in the second. And so what I'm really saying here is, what is the total effect of both surfaces? That's what a lens is. A lens has both surfaces. And I'm going to make a few special cases here. You'll already notice the first special case is I'm starting in air. That's where the ones came from. And finishing in air. And so what I'm about to come up with would only be true for a lens that would have air on both sides. What I'm about to say next is, let's say T is small. Let's say we have a surface 1 and surface 2, so the thickness is not much. You saw it in your book as the thin lens equation. So what we're about to come up with next is the thin lens equation. Not only is it a small angle approximation, but it's also true only if the lens is fairly thin. And fortunately that's true because it doesn't really show it in my drawing, but the image formed from this first surface would really be way over here for most surfaces. And the thickness T would be much smaller compared to where the image is formed. And so I say that because then the magnitude of the image formed from the first one is equal to the magnitude of the object distance. Now, why do I say magnitude? Because watch your signs, right? If the image from the first one is formed way over here, then that Q1 is positive. But what sign would we want for P2? Negative. So really the negative of Q1 is what P2 is. That's what I want to get you to see. So again, caution for this special case. This is a special case where we start in air, we finish in air. It's also a special case in the sense that the thickness of the lens is really small. That's why it's called the thin lens equation. But if we're willing to accept all that, and we're willing to take an object created, or excuse me, an image created from our first surface, becoming the object for our second, then watch what happens. I will solve for n over Q1 from that first surface. And so the first surface becomes this. I will solve this one for n over P2, which then becomes 1 minus n over R2 minus 1 over Q2. Hopefully you're seeing that these two are almost the same thing except for the minus sign when we put those together, right? This really is the negative of n over P2. That's what this statement is making. So you can see there's a lot behind there. That's why I felt like I know we got to get out of this chapter, but I'd like you to see this. If you put that then together, what we have is this one, 1 over n1 over r2 minus 1 over q2. So that's this equation. Has to equal the negative of this equation. So the negative of this equation. And now, if you do a little more algebra, we're done. This becomes 1 over P1, positive. This over here becomes 1 over Q2. When you move this to the other side, you get an n minus 1, 1 over R1. And this one, by taking the negative of it, will allow that term to look like that term and factor out. And if you're willing to call all of this 1 over f, then don't we have the lens equation that we've been talking about? If you're willing to put the two surfaces together, if you're willing to accept the special case where you start in air, you finish in air, the lens is fairly thin, then 1 over object distance plus 1 over image distance. And this is the final image. This is image number 2. This is the beginning object. Equals 1 over the focal length. That was the grand finale of last lecture that I wanted to start here today to say, yes, this equation does work for a lens. This right here is how you would find the focal length. And so we could say that the focal length is r over 2 for a mirror, but for a lens, it's not so pretty. And that's why it's referred to as the LensMaker equation. It involves both radius of curvatures. Makes sense. The light bends on both surfaces. And it depends on the index of refraction. Again, makes sense. The bending occurs because of that. So that's why I saved this towards the end, that this equation is good for all 10 cases. When it comes to mirrors, this would be the relationship of the focal length and the radius of curvature. When it comes to lenses, that would be the equation. And it's a more complicated equation, and it's the one that I didn't get a chance to give you last time, and I thought it would be enlightening to go through and see how the image is formed from the first surface, and then that forms an image. That image becomes the object for the second surface, and where this equation comes from. And you can see why then we call this the LensMaker equation. If somebody wanted to make a lens and you wanted to have it a certain focal length, these are the three things you have to work with. The radius of curvature of each side and the index of the material it's made out of. Yeah.
So the question is that Q1 minus T distance?
Yeah.
That's the new P, right?
And that's going to become the new P. But if T is 0,
Is that actual distance that you underline Q1 minus T, or is that shorter distance actually?
good point. Originally, Q, this is Q,
Yes.
and then this is T. So as you are pointing out, this is the Q minus the T. Yeah. And we've got other things to do, so again, this is just our introduction to optics. But you can see how this could get more complicated. What if you don't have a thin lens? Well, if you don't have a thin lens, you need to do both refracting surfaces twice. That's how you handle it. If it is a thin lens, well, you can just jump onto this equation. And so the equation we have is the special case, a thin lens. It's also the special case where you start in air and you finish in air. But what if we have a lens that's not in the air? What if this is a lens underwater? How are we going to handle it? Well, we'd have to go back and rederive it, right? It wouldn't work here. We would have to put the index number 1 here. And maybe we would go from one material, like water, into a lens and then into air. And so the material on the other side isn't the same. And so we can answer all of those, but that's a little more than where we want to go this semester. I just wanted you to see that this equation would work. It also works for the lenses. The focal length is determined by the radius of curvature. And although this equation is kind of limited for the lenses are more complex. This equation would only work for a thin lens. It would only work when you start in air and you finish in air. It also has a small angle approximation, but like I said, it's a good place for us to begin our optics, and later on, depending on what you go into, you may expand on this a little further. I say that because then, if we look at some of these lenses, we could design lenses different ways. You saw in class this one, the biconvex, and the plano-convex. I put both of those up there on the board and we watched the light converge. Both of those made the light converge. Both of those had a positive focal length. And if we look closely then at this mathematics, hopefully it will make sense. I'll start with n minus 1. n minus 1, is that a positive number or a negative number? It's going to be positive. Whatever this lens is made out of, chances are it's glass, or some other, more exotic, like my lenses are what they call high index glass, so the index is like 1.7. But whatever it is, it's going to be a positive number, that's for sure. So whether f comes out to be positive or negative is really determined here in this equation. So let me start with this biconvex. As the light comes in and hits the first surface, that r would be a positive number. So when I go 1 divided by r, that's a positive number. Minus what? Well, look at the second surface. Which way is the curvature? Where the light is coming from, not where it's going. So r is a negative number. So when you go minus a negative number, that too is positive. And so positive, positive, and positive all together make a positive. So it doesn't surprise me that this shape had a positive focal length and the light converged. In fact, it doesn't surprise me also that this one came out to be positive, because this one would have a positive here, a positive on the first surface, and this would essentially be 1 over infinity on the flat surface. So I have a positive minus 0. Well, that's still positive. And so again, doesn't surprise me that that one is positive. How about this one?
One of those R's is actually positive, it's actually negative.
Is it? Let's look at the R's.
They're both facing the
They're both the same way, aren't they? Are they both positive, both negative? They're both positive. And so I think this one can throw you off a little bit because this one is both positive. It is 1 over R1 minus 1 over R2. And so you have a positive minus a positive. Does that come out to be a positive or a negative? Depends which one's bigger, right? So look closely at this. Which R is bigger? The first surface or the second?
The second surface is bigger because it has to curve.
Right. I would say if this is the first surface, that's terrible. That's the second surface, right? There's my lens. So R2 is bigger than R1. The fact that it gets pinched off on this edge can only occur if R2 is greater than R1. Now, a consequence of R2 being bigger than R1 means that 1 over R1 is bigger than 1 over R2. And so it is, this first term is a more positive than this term is a negative. And the overall result is this is positive. And this lens then, all of these lenses are all positive. They all make the light converge. I think this one's a little bit harder to see, but it does make the light converge. I asked Don for his reading glasses here because reading glasses magnify things. And as we learned, that is a great shape for magnifying. But this is a terrible shape to put on somebody's face. That matches the contour of their face much nicer. And so reading glasses or farsighted people will have a lens in this way because you need the conversion of the light, and you want to get that and yet still match the contour of your face. So if I were to put these glasses up here in the overhead, what do you see on the image here? Yeah, you can see that it has made the light converge. And so this has a focal length maybe about there.
Careful, you don't.
Burn a hole in it? It's not that bright.
That's probably right around your eyes.
Think so? All right, okay, I won't look at it.
So basically, so bottom line saying that R1, the 1 over R1 minus 1 over R2 does not, there's no need to change the negative or anything of that nature, right?
Well, what I guess I am going to say, though, and maybe I should pull up the table, is be careful with your signs. Table 2 is the one that listed sign convention for refracting surface, R. R is positive when the center of curvature is in the back of the surface, when the center of curvature is front of the surface. Okay? So the equation is great. Don't mess with the equation. The minus sign is appropriate. Just put in the appropriate plus or minus for R2 and the appropriate plus or minus for R1, and then you will get the appropriate focal length. And then once you get the appropriate focal length, you will then be able to get the P and the Q. Okay? And so some problems, they will give you the focal length, whether it be the focal length of a mirror or whether it be the focal length of the lens, and then you can continue on with the problem, no issues. But other problems, they will tell you it's a mirror and give you its radius of curvature, or they will tell you it's a thin lens used in the air, and they will say then the radius of curvature of the two surfaces, and from that you can get the focal length and then continue on into the problem. And again, that's why it's called the LensMaker equation. You want to know what the focal length needs to be, and it's based upon the shape of the lens. You have to make the lens. Yeah.
So R2 is really just, so R2 is actually negative for biconvex, and for concave convex, it's positive.
Let's see, did I hear what you, so in this case, R1 is positive and R2 is negative. In this case, R1 is positive and R2 is positive. In this case, R1 is positive, and R2 is infinity.
It's 0 because of this.
1 over infinity, yeah. And infinity, positive or negative, doesn't really matter at that point, right? But let's do a compare and contrast to this. This is the shape that I showed you. I showed you this shape and this shape in class. Those were the two I had to show you. And I showed you that the light diverged. I showed you this scenario. I showed you where the focal length was the equivalent of being less than 0, making the light diverge. Maybe now you can see it in the math. If you stand over here and you look, R1 and R2, let's look at this. As the light comes in, R1 is positive or negative? Negative. R2 is positive or negative? Positive. And so if you put a 1 over a negative, that's negative. You subtract a 1 over a positive, that whole thing is negative. That makes altogether a negative. And so this is what I would call double negative, right? They both make it diverge. That's why it's the one I showed you. It's the one you'll be working in the lab this week with. How about that one? It comes out to be -2 because the first one is 1 over R1, which is a negative number, and then the next one is 1 over infinity. So you get a negative overall. But again, something like this, as the light comes in, R1 is positive. R2 is positive. They're both positive, right? They're both on this side of the lens. And so the question becomes, does the overall equation give you a positive number or a negative number? And it depends on your radius of curvature. So maybe I'll leave that drawing there and take a closer look at this one. In this one, I have a big R1 and a smaller R2. And so R1 is positive, but it is bigger than R2, which is also positive. But since this one is smaller, 1 over a smaller number is more negative than this one is positive, and the overall is negative. So again, this one could come out to be a negative. And this again would be one that would be more appropriate to go on somebody's face. It has the same effect as this one or this one in the sense that it makes the light diverge, but its shape is more appropriate for eyeglasses, and that's the one I was showing you. I'm nearsighted, and so this will make the light diverge. And so if I were to put this on the board, you can see that the light comes in through this lens and then spreads out.
So in convex concave, the second surface has a smaller radius of curvature, and the outer side has a larger radius of curvature?
For this one here, the convex concave, right? R1 is big and R2 is small. I like to remember it this way. If you come back to this one, anytime you're going to pinch off the edges, that means R2 has to be smaller to pinch off the edges. And so anything that pinches on the edges has got to be a converging lens, has to be a positive lens. But anything that is fatter on the ends than in the center means that R2 is smaller than R1. And so this type of lens tends to be fat on the center.
Unless you cut off the edges of the bottom one, you still have
Well, wherever you cut the lens, even if you cut it here, it doesn't have to pinch it off, but it's still thinner at the end than it is in the middle. Whereas this one, wherever you cut it off, it's always going to be fatter at the ends than in the centers. Again, I think that's why these type of glasses look a little better on people's faces, because they're not so thick at the edges. Nearsighted, you got a thick edge so that you can keep the center thick enough that it doesn't break. Which is why I always get mine polished on the edge there, so they don't look so, thick, and pay the extra whatever $50. Rob me. But that way, that way it doesn't look so thick. And also, like I said, you can have the higher index. And again, that's what I bother to do, is get the little higher index so they're not as thick and they're not as heavy, and then they're just, lightweight, and I don't have to worry about breaking them with kids kicking me with a soccer ball. Last night, I turned around, a soccer ball hit me across the face there. So you never know what's coming in my house. So, and so there's the different lenses there. All right, well, I said a lot. Real quickly then, let me just point out 2 quick problems, and then we better move into the next chapter here. But I did, at least kind of indirectly, quite a few examples and ideas that be careful in calculating the object and image distance. Be careful with your sign. And when something gets more complicated, where you have multiple mirrors or multiple lenses, just remember that the image from one becomes the object to the next. That's why tomorrow's lab, although a little bit long, hopefully you will enjoy, because you will put one lens and another lens and another lens, and you will mix it up, and you will do this mirror and then this lens and then this mirror. And if you really understand the equations behind this, the lab will go pretty quick. If you don't, it takes a long time, but you'll learn a lot along the way. There's 3 main parts of mixing the lenses and the labs, and finding the focal length and calculating the image distance. And it's a really good exercise. So I'm going to use the lab for most of the learning by examples, but I did point out that if I grab, and I think it's number 64, 64 is a really good example because it's just got a lot of everything put together. It's a magenta problem, so you can imagine that they've kind of given you the top end of everything we're going to do. And so if I can find number 64 somewhere, here is the end of this chapter. Boy, long chapter. All right, here we go. 64, finally. All right, so number 64 says this. It says figure 64. In fact, maybe I'll just even call up figure 64 so you can kind of look at it while I'm I passed it again. Problem, 64. There we go. All right. And so it has a lens, it has a mirror, and somebody's looking at it here. And here's what it says. It says, figure 64 shows a thin converging lens for which the radius of curvature of the first surface is 9, and the radius of curvature of the second one is 11. So they give you the radius of curvature. The lens is in front of a concave spherical mirror with a radius of 8 centimeters. A. Assuming that the focal lengths of f1 and f2 are 5 centimeters from the center of the lens, what is the index of refraction? Okay, so the first part here is really using the lens equation that we just derived. Noting the radius of curvatures and the index, we can get f, although in this case, they gave us the radius, they gave us the focal length, and they asked us to find n. All right, so as I read it again here with a little more careful in the numbers, they do say that assuming that the focal lengths f1 and f2, oh, that's bad notation. Can a lens ever have a different focal length on one side versus the other? No, I was trying to say that. So that notation alone tends to imply that, and that's too bad. It should be just the focal length. It's on both sides, yes, because the light can go left to right or right to left, but it's only going to ever have one value. That's too bad. Anyways, so they say the focal length is 5. And they put 5 centimeters. So I will put 5 centimeters here, being careful with my units. They then say the first radius of curvature, and so I suppose they're talking about this one. Yeah.
Maybe they meant like R1, R2. Yeah.
Yeah, okay, I'm not even going to guess then what they're thinking, but this should come out to be 5. The focal length should come out to be 5 because of the both surfaces. And then they told me the radius of the two surfaces. It's not exactly symmetric. It has a 9 on one and an 11 on the other. And so this is 1 over 9. And so the light comes in, hits right here, and I'm just going to ask you, positive or negative number for R?
Negative on the other side.
It's positive, right? If the light is coming from this way.
Oh, that. Oh, the other. The negative on the
Right? And it should be, right? Here's the object. Light's going to come to here, so this is a positive 9. What about this surface? Positive number or negative number? It's negative, so I'm going to put in a negative 11. Right? And so the two negatives, of course, make a positive, yeah.
Why do we assume the light's coming from the eye? Wouldn't it be the other way?
No, it's not coming from the eye. I'm sorry. I haven't read all the question, but what's going to happen here is the light goes through this optical system. What does this person see? That's the question.
Where is the object? Right there, whatever.
This is the object.
Okay.
So this is a can of shaving cream going through a lens, bouncing off a mirror. And of course, why it's magenta is to realize it's going to go through the mirror again. I mean, lens again, and then to the eye. So what does that person see? How big is it and whatnot? Okay. But that's why I would say it would go that way. I'll reverse it if you want. Because eventually, isn't the light going to go through here, hit the mirror, and come this way? All right. So what would be the focal length if it went the other direction? Well, I'm telling you it would still come out to be 5. In case you don't believe it, let me try. What if the light was coming from the other direction? If it comes from this direction, it would hit this surface first, which has a curvature of 11. Would it be a positive number or a negative number? It's positive. So I would get 1 over a positive 11 minus, and then it would hit this surface, which we said was a 9. Positive number or negative number? Negative. So 1 over a negative 9. So that's why I was saying a focal length of a lens always comes out to be the same number. When you reverse the order, you reverse 1 and 2, but you also reverse the sign of 1 and 2. And so you get the same focal length, and you can see that in the math. This and this are exactly the same equation. So either way the light is going doesn't really matter. You're going to get the same index of n. You're going to get the same focal length. Yeah.
The best way to think about R as negative or positive is if it enters and leaves the surface of it, the radius. Like if it leaves the surface with the radius, then it's negative. If it enters the surface with the radius, then it's positive.
Okay, if that helps you. I just like to say wherever the light goes is the positive side. Okay, so as the light goes through the lens, it's positive. As it hits the mirror and bounces off, where it goes is the positive side. Where the light goes, whether it be a mirror, whether it be a lens, whether it be just a single refracting surface, where does the light go? All right, well now we got a little bit of math to do in order to come up with n. And so let's see. 11 reciprocal plus 9 reciprocal equals. And then if I take that number and multiply it by 5, I get that number down there. Reciprocal of that. Uh-oh. What did I do wrong? One divided by 11 plus 1 divided by 9. Did I 0.202? Did I mix up my units? What's the focal length, they said? Focal length is 5 centimeters. Radiuses are 5. .2.
I got 0.02
So 0.2 divided by point, did you get 202 there?
I got .040.
Point what?
04. Oh, I mean, if you divide those, I guess it's the same thing. .2.
All right, I'm messing up big time here. 1 into 5.
Everything you have is correct. Just divide off the .202.
Well, okay, maybe I should just keep going. I'm not liking this.
I get it. It is 1.99.
Oh, is that okay? So maybe I should just keep going. Okay, maybe okay. Just trying to do too much in my head. So is that what you got about it too? Yeah. Oh, okay. All right. Good. All right. So n is 1.99. Okay, good. I didn't mess up. I just need to shut up and just do the numbers. Okay. All right. And try to look ahead. Anyways, but there would be the problem. What is the index? And so it is a little high. I guess that's what was bothering me. I was thinking we would kind of come up something like glass, but it's a little high, but so be it. That's the numbers that they built this out of, has a high index. And that's the first question, and the first one I wanted to show you. Then B says, the lens and the mirror are then 20 centimeters apart, and an object is then placed 8 centimeters to the left of the lens. Determine the position of the final image and the magnification as seen by the human eye in the figure. And then finally C, is this image inverted or is it upright? Okay. All right. So they've given me some numbers where this is 20 centimeters. They've already told me that the focal length of each of them is, no, focal length of this one is 5 for the lens. The other piece I'd like to know is what is the focal length of the mirror? Yeah, I thought they gave me R in here. Now I'm going back. The thin lens has a radius of 1 and 2. Okay. The lens is in front of a... There it is. Okay. The concave spherical mirror has a radius of curvature of 8. All right. So the R of the mirror is 8. So the focal length is 4. Okay. And so again, using the radius of curvature... Oh, I erased it. Well, this one's still here. But the focal length of a mirror is half the radius of curvature. That was the easy one. But the focal length of the lens is a little more complicated. We got to use the LensMaker equation for that one. Now, knowing that, then I can put some numbers into here. They gave me the image. Let me go back and read this one. You can see why it's a magenta. But like I said, I thought if we worked through this, I'll pretty much cover everything, is that the object is placed 8 centimeters from the lens. So if I start off and I do my first calculation for the lens, so I will say lens, I will have a 1 over 8 plus a 1 over unknown and a 1 over 5 for the calculation for where is the image. And so if I grab my calculator here, I got 5, the reciprocal, minus 8 reciprocal. Take the reciprocal of that, and we're looking at about a 13.3, and I'm doing everything in centimeters, and that's a positive number. And so that tells me that the image is maybe here. And I guess I should ask, is it upside down? Is it bigger? Is it smaller? Okay, so we learned if the object was farther away than the focal length, it would form a real image. Good.
It should be upside down.
And a real image would be upside down. Okay? And we also learned if it was more than twice the focal length, which if that's a 5, it's not twice the focal length. But if it was more than twice the focal length, it would be upside down and smaller. This is less than that, so this is upside down and bigger. So if I do what I would call magnification number 1, how big is this? I would have a minus q over a p. This is minus a 13.3 over an 8. And so 13.3333 divided by 8 gives me a magnification of 1 2/3. So it is upside down and is a little bit bigger. And so if I were to draw it, it would be something like that.
Why wouldn't it be negative?
Oh, thank you. Yeah, negative, upside down. Yeah. All right. Now that it is upside down, let's go to the next one. And so then we go to the mirror. Okay? And so the mirror, the object from the first one becomes the image of the next one here. Or the image of the first one becomes the object for the next one here. So if I go to write this as 1 over p plus 1 over q equals 1 over the focal length, I have the focal length already. That's a 4. I'd like to find where is the image from this mirror. I need then the object distance. So what would this be? Oh, good. And so if I take the whole distance between them and subtract the 13 1/3, is that a 6 2/3?
Wait, what's the 13.3 on the picture?
The 13.3 is image distance. So this is 13.3. The distance that the image is, and again, remember everything is measured from the surface of that lens or mirror. So that's my 13. So knowing this whole thing is a 20, that's why I subtract the 13. Okay? So keeping that in mind, I can come up with my Q. And so for reciprocal minus 6.66666 reciprocal equals reciprocal of that comes out to be a 10. And it's a positive 10. Which hopefully makes sense, because what did we learn about the mirrors? If we were outside the focal length, we would get a real image, right? And if we were between the focal length and the radius of curvature, which we are, that's kind of what happened here, we should get what? Inverted and magnified. And so sure enough, I have got a positive number. And if I look at the magnification of number 2, minus p over q, that would be a minus a positive 10. And the q was the 6 2/3. And so I get my 10 divided by 6 2/3, coming up with 1.5. And so now, the image formed from the mirror is right about here. Halfway between, because it's 10 from the mirror, and it's on the positive side. And this is 1.5 times bigger than this. And this is already 1 2/3 bigger than that. So if I multiplied those two magnifications together, that would tell me how much times bigger that is than that. But I'm not even going to do that yet, because it's still got to go through another optical element, and I'll just wait until the third time. Yeah.
Besides memorizing that table, could we just draw the rays and find out whether it was bigger and magnified or?
Oh, sure. Yeah. In fact, you tempt me to draw the rays on there, but I think I'll make things worse if I also draw rays on there. Okay. So maybe I should put then, this is 10. this is what I would call Q number 2, and this is Q number 1. Right? And then finally, I can get the last step here by, again, writing what's going to happen next, which the light re-enters that lens. And what I was trying to emphasize so much is this equation will work for all of them. Okay? Actually, I'm glad you bring up drawing the rays, because that's what kind of makes the lab a little long tomorrow. You want to draw the rays carefully and accurately and measure it, and then you want to calculate it and see if they match. And so that's, the lab where you draw it, you calculate it, do they match? And if, of course, they don't match, that means you're doing something wrong, and compare it like we do in a lot of our labs. Yeah. Say, okay, what am I not understanding here? All right, so the last step then is to go ahead and put this into the equation. Again, my P would be a 10, and it would be a positive 10. The P is the distance, how far is the object from this lens. And remember my object being defined as the image from this mirror. Okay? And so that's 10 away. I can then find out what is my image location by remembering that the focal length of that lens is a 5. And so 5 reciprocal minus 10 reciprocal equals, and reciprocal of that is another 10. And so that's a positive 10. If I look at this magnification, which maybe I will call magnification number 3, which is minus a Q over a P, then I've got a negative 10 over a 10, which is just a negative 1. So that flips it upside down again, but doesn't make it bigger or smaller. And so that means if this was 8, 10 is probably right about here. And then hopefully that's in agreement with that one we saw with the ping pong ball. Remember I said when the ping pong ball was right at the radius of curvature, what it does is invert it but give it the same size. That's what we have here. We have this one, which is twice the focal length of the lens. So anything when the object is twice the focal length, it will give exactly the same size but upside down at twice the focal length. So that's that unique solution. Yeah.
Is there any practical setup? Is there any practical application to this setup? Because the only thing I can think of is using with a telescope. It bounces in, bounces off the mirror, then bounces off into a smaller mirror and bounces into an eyepiece at a 90-degree angle. That's
Well, I cannot think of any direct application this particular setup needs, because we go through it 3 times. But if we only did it twice, this is a perfect example of a telescope, because that's what a telescope would do. The light comes in and hits the mirror and then goes through the eyepiece, and then the magnification is just the 2 of them. And if you want more magnification, just change the optics of those 2. Don't have a third one. That make sense? Yeah. So in this case, whatever you're looking at is actually in front of you. So, and your optics is behind that. I don't know, maybe there are situations where you have something tiny that you can't, I don't know, get a microscope in front of. I can't think of one, but you put it behind it and you get the magnification.
Yeah, so now it appears to be 2 centimeters closer.
Oh, right. So it appears a little bit closer. As you said, 2 centimeters closer. And it also, the other question was, not only where is it, but is it upside down? And I would say overall it's upside down compared to where it started, right? Because the first one, upside down, the next one, right at it, and then the next one, upside down again. So the overall effect is it is upside down. So whatever I have here in front of me and I put my optics behind me, the image I see is going to now be bigger, closer, and upside down. And of course the last part of this question is how much bigger? Yeah.
Are you going to see 2 images? Or are you going to see the actual object in front of it?
No, well, you wouldn't of course see these.
No, I mean like right, the objects in front, so you have the actual physical object.
Right. So it would be like
You
that.
have like the second, the magnified image.
Right. So you would see the 2 of them a lot like, remember the ping pong ball I had in the mirror? You saw the original ping pong ball. So there's the original ping pong ball. And then you also see the image created from your optic. So you see 2. You see the original and you see the image. You don't see these. These lights have been redirected. Okay. All right. So the final question is how big is the overall magnification, and so that would be M1 times M2 times M3. And so the first one was magnified by a negative 1.6666. The second one was magnified by a negative 1.5. And the third one was magnified by a negative 1. That's how we get an overall negative. 3 negatives overall make a negative. And together, we're at 2.5. So it's 2.5 times bigger, upside down, 2 centimeters closer. That answers your question. Now, keeping that in mind, and needing to go to the next chapter, let me just look and read number 36. But I want to remind you of your mechanics that I've seen in the past. Students on a problem like this get confused. Here's what it says. It says that you have an antelope in your camera lens. An antelope is a distance of 20 meters from a converging lens that has a focal length of 30. The lens then forms an image of this animal on your CCD array in your camera. The antelope is spooked. It runs away from the camera. If the antelope is running away at a speed of 5 meters per second, how fast is the image moving?
It's scaled down, isn't it?
Did you catch that? Not where is the image, not how big is the image, how fast is the image moving. Right, so go back to our mechanics. If you know position,
What number is this?
don't you also know velocities and accelerations? And so work on that. Your question is what number? 36. Okay? And I'm not going to take the time to do the whole problem, but I am going to say that just remember your mechanics. How do you go from position to velocity? You take the derivative, right? So if I were to take this whole equation and take the derivative with respect to time, maybe it's best to write it as P inverse Q inverse over F, or equals F inverse. And then take the derivative with respect to time. Yeah?
Couldn't you just find your magnification and multiply that by the original speed?
I don't think it comes out that simple. Why would you say it does? I mean, maybe it's worthwhile to go and prove that. Not now. But I don't think that it comes out that simple. I mean, I see why you're thinking that. But my question to you is, why? Prove that to me. And this would be the proof. What you would do is take the derivative. You would say, that comes out to be a negative 1 over p squared dp dt. This becomes a negative 1 over q squared dq dt. And that equals 0. Exactly. And so, it looks like I got magnification squared. Because I would call this what? Well, dp dt is the velocity of the object. What's dq dt? The velocity of the image. And so rewriting this maybe as a negative 1 over p squared dp dt equaling positive 1 over q squared dq dt, putting the q squared over to here, I guess what I get is the velocity of the image is the velocity of the object times the magnification squared with a negative. So it was close to what your gut was telling you, but it was actually the square root of the magnification. And anyways, I just wanted to remind you that you could do the velocity and the acceleration of the image, right? And the if you know the object. All right, well, like I said, wanted to take the first hour, and that was an hour and a half, so we're even more behind than we got started here. But let's switch gears here for just a moment and look at our web. Oh, isn't that wonderful? Look at that. City College. #1 in the United States. All right. And look at, what am I after? Our web page. No. Academic departments. Physics. Here. And where's our web page? All right. So coming down here to our flash physics, let's take a look at some optics here. And we are going to start, for the first time, as we get into this next chapter, of looking at, not that one, a double slit. That one's a little earlier. Where's the double slit interference? That one. Okay? And so here's where I want to begin the next chapter. In fact, I want to begin the next chapter by kind of giving a highlight of the 4 chapters that we are doing here with the optics and see how far we get here. Fortunately, these next 2 aren't nearly as long. Yeah?
You have negative of the magnification squared, but since Q is negative, wouldn't dq dt cancel out that negative?
Wait, would...
Because the image was virtual on the mirror, right? Or was it the lens?
Q would have came out to be a positive. I didn't actually calculate a number.
Okay.
But since our object was 20 meters away, it was well outside of the focal length. So our Q would come out to be a positive number. Yeah. In fact, bummer, I'll go back. But this is really what you are saying. Here's a good animation that I wanted to show you, and I guess I will here, of the rays. If I have something that looks like this, here is the object. As you draw it through, and they've drawn these 2. For you guys in class, I like to draw this one. But there is the image. This animation, I think, shows really well the relationship. Here, as you bring it in, the image moves further out. So as P gets smaller, Q gets bigger, which doesn't surprise you, given that 1 over P plus 1 over Q has to equals 1 over F. That F doesn't change. So if one gets bigger, the other one's got to get smaller. Yeah.
Wait, if the speed goes into dp dt, then what goes into q squared and 4p squared? Like the p initial or something of that nature?
Well, P and Q are the positions at that moment. And those 2, of course, why it's running would change with time, but you would have to then calculate, not only what is the speed of the antelope at that moment, but what is the position of that antelope.
Oh, the speed changes as it gets farther and farther away.
Well, I'm not sure the speed of the object changes, but the position of the object changes. Therefore, the velocity of the image changes.
It's not constant velocity.
Okay, now watch this. Here is the problem. This little light is not an antelope, but it is going to move away from the lens. Watch the image. Oh, first it goes closer, sorry. Closer still. Now it goes away. And so it's going away at roughly a constant speed, but because of the mathematics of the reciprocals, there is a non-linear relationship between the speed of the object and the speed of the image. Yeah.
So if we were to draw the rays like I was asking before,
Yeah.
so it goes parallel and then through the focal point,
One goes parallel to the focal point, yes.
and then one just goes straight to the center.
Well, that's not the one I showed you, but yes, one does go through the center. That's what this animation is doing. I showed you another one, the one that goes through this focal point, then goes parallel. And I like the two that go through the focal point. But you only need two. And it's probably good to see all three. And this, like I said, this animation shows all three. Which, by the way, as you do the lab tomorrow, I will show you this one. You draw the rays that are created from the first one. Then you put the second lens there, realizing that the light has been affected by this second lens before it gets here. And then you have to draw the rays of what happens next. It's the very last problem in the lab. Maybe I showed you this too early. I usually like to let you struggle for a while and then go, here, let me show you something on the computer that will help you draw these. But you were supposed to do a calculation and a ray drawing, and that's the grand finale of it. All right, so now, hopefully, back to this picture. And back to what I was trying to get started here, and say, as we are doing our optics, and as you can see, it's just a small introduction to optics, just like all of ours. I mean, we did thermodynamics. There just wasn't enough time to do all our thermodynamics. That's why you are lucky enough to have another class on thermodynamics when you transfer. Almost all of you. Very few of you will probably take an extended class in optics, but many of you will. And of course, that's this goal, is to get you familiar with the basics of optics. And I would say at this point, we have done what we call ray optics. We have let our rays bend according to Snell's law. We have not dealt with the fact that they are waves, and when waves come together, can't they have other properties that we learned before about constructive and destructive interference? And that's what we're about to deal with next. And so, in chapters 37 and 38, we will treat our light as waves now. Instead of little photons that travel along in straight lines and make up rays, we will take the other approach, that they can also be modeled as waves, and the consequences of that we will see in terms of interference and other properties that waves have. And so this chapter, chapter 37, is what we will spend, well, the rest of today and Thursday and maybe a little time into Tuesday. But fortunately, it's not a too long of chapter. It's all about interference of the waves, and we've already done interference. Now, granted, we did it back in February, but when we did those waves, we dealt with our interference. Whereas in 38, then, we will get into a property called diffraction, and a property called polarization, and that might be the part we're going to have to truncate. Hopefully we'll do a little bit of that, but at least we'll kind of introduce that. And so let me talk here about interference. In fact, it's kind of weird to say this, but even though I'm not going to talk about diffraction, I got to show you diffraction before we can even get to interference. So what is diffraction? Well, the diffraction here is the spreading of waves. I don't know if you noticed this little animation real carefully here, but it's an animation trying to say this, that if you had a big broad beam, which in my case, my big broad laser beam is going to be right here on the wall, 3 centimeters wide. Okay, so here's my laser beam. You can follow it back, right? And it's coming from this little tube here. All right, so this is supposed to represent my laser beam. So my laser beam goes shooting out. What if I were to send that light through an opening, a hole? Or maybe I should call it a slit versus a hole, because it's going to be really tall but very narrow. And you saw this kind of before when we got started in 35. Here is my hole. And I would claim that this is a slit more than a hole, and it's a pretty wide slit. And if I were to put this laser beam through the hole, probably doesn't surprise you that it goes right through and really nothing happens. And I would consider that a ray or a particle model here, that these are photons, they go straight through. But something interesting happens when that hole gets small. Like I said, it's called diffraction, and the light spreads out. I'm not going to try to explain it until we get to chapter 38. I'm going to try to explain interference because that will help us understand this first. But I have to actually use this to talk about this. And so it's kind of a weird setup here. But it does work best that way. Trust me here that I just won't even try to explain why there's diffraction. I will just show it to you. And so you saw it before. If I go ahead and I make this slit really, really small, and I'm not sure that's small enough yet. It's a little small. But as I make it small, of course, it gets pretty dim. So it's going to be harder to see. So I'll power down the lights here. But as I look at it now, doesn't it look spread out? In fact, I'll move the slit out of the way. See, there's the regular beam, 3 millimeters wide. But as I put it through a small slit, it spreads out. Now, that slit is still, I would say, pretty big. It only spread out a little bit. So if I make the slit even smaller, of course, it's going to get dimmer, which is going to make it harder to see. It's going to make it harder to find the opening. Ah, there it is. But would you agree it spreads out quite a bit? And that's what this animation is trying to say. If you were to shine light into a small hole, it would spread out. Now, the spreading out here is much more pronounced than what I'm showing you. I can't make a slit quite that small and still have enough intensity unless, I guess, I turn everything off. We're just not gonna see it. But I think you can at least get us started by saying, see how the light spreads out when it goes through a little hole? Here's why I care about that. What if I shine it through 2 holes? Right, and that's the beginning of this chapter. What we essentially have now is 2 openings, 2 sets of waves spreading out. And what do we know about when waves come together? Superpositioning, right? They will interfere. And so what you are hopefully seeing here in this animation is that the black lines are supposed to represent the troughs, and the brighter lines the crest. And so as they go across, you will see that maybe way over here, you are getting a wave from the first opening and a wave from the second opening. And when those 2 waves come together, depending on how they come together, you will get constructive or destructive interference. And so right here, what I would call the center, there would be a certain number of waves, but whatever that number is, it would be the same as those. Now, this is red light, so its wavelength is probably closer to 600 nanometers. Let me just kind of round that to the middle. It would be green somewhere or yellow. I'll go 500. Maybe that's even closer to the blue. But if I go 500, the reason 500 makes a nice number. 500 nanometers means that there are 6 million waves in 1 meter. Okay, so if I stand 1, 2, 3, 4 meters away, how many waves lengths do I have between this screen and back to my opening? Well, there's about 2 million times 4, so about 8 million wavelengths. Fair enough? As you'll see, I don't really care how many total there is. But if you're going to get constructive interference, don't you care about whether or not they're the same or different? That's going to be the key. In fact, that's going to be the key to the whole chapter. You want the answer to everything in this chapter? It's the interference between waves. Look at the difference between the 2 paths. Yeah?
Where does the 6 million come from?
Wait, did I say 2 million? Maybe I better check my math here. If I have 1 meter, and the wavelength is 500 nanometers, which I can write as 5 times 10 to the minus 7. 1 over 5 is 0.2, 10 to the 7th. So isn't that 2 times 10 to the 6th? So there's 2 million in 1 meter. Okay? And there's about 4 meters. So 4 times 2 is 8 million. If I said 6, I'm sorry. I guess I mean 8 million. Again, not worried about the exact number. I'm worried about the difference between the two. And here's what I'm trying to say, is right here in the center, there would be 8 million wavelengths here, 8 million here, and when one wave came and hit the screen with a crest, the other wave would hit with a crest. And what would I get at that point? When crests line up, I get constructive. I would expect bright. However, as I move along the screen, which in this diagram would be up, on this screen would be over, what's eventually going to happen as I move away from the center? Right about here in this animation. And what I'm saying here is as I move up, aren't I a hair closer to that opening compared to that opening? And so, if there is 8 million waves here, there is 8 million and a half. And what's going to happen? They're going to differ by a half a wavelength. And the crest of one is going to line up with the trough of the other. And again, what did we learn way back in February about when you have two waves lined up where the crest of one lines up with the trough of the other? What happens? You get destructive. And when it comes to light, destructive means what? Dim, no light. I'll keep going with this animation, but let's just see if we can see it on the screen. I happen to have two tiny slits. If I were to shine the beam through here and display it on the screen, might even help to have the light dimmed here. What do you see on this far wall? Do you see what we're going to call a fringe pattern, an interference pattern? You see down the center. Down the center is what I was saying is right here where you get constructive interference. You get 8 million waves here and 8 million waves there. Crests line up with crest, and it's going to be really bright in the center. But as you move to the left or to the right, and in this little animation it's either up or down, but over here it's left or right, as I slightly move to the left or to the right, then what's going to happen is the distance from one opening to the other is slightly different. If that slight difference is one wavelength, now remember, it doesn't have to be very far. One wavelength is not very far. But if you move, I'm sorry, 1/2 a wavelength. If you move 1/2 a wavelength, you will now get destructive interference. And so coming back to the screen here, this dark spot represents then where one, the bottom one in this case, is 1/2 a wavelength further than that one. And then, keep going. What if I go up the screen a little bit further? What's going to happen here? It's going to get bright again. Why? I get constructive. Why? Right, because the path difference is not the same. And you can see that the bottom one has to travel further than the top one. But if that bottom one travels one whole wavelength more, so again, if the top one is 8 million and the bottom is 8 million and 1, then how will those waves line up? Yep, trough to trough and crest to crest, and you will get constructive interference. And so coming back to this picture, you will see where it gets bright again. And that whole pattern continues. Bright, dark, bright, dark, bright, dark, bright, dark. But I'll keep going with this animation. In fact, the first person to do this was a scientist with brilliant name. It's called Young's double slit experiment, right? and his argument was that he could prove that light was a wave. And of course, now, as you said, we call these wavicles, you know. And so they're really both, because there's a lot of experiments I can do that would verify that they act like waves, but there's also a lot of other experiments I can do that verify that they are particles. In fact, interesting enough, I saw one of my students, no, not this class, yesterday, outside of the school setting. I was stuck in traffic at the light driving, and it just dawned on me. I said, oh, here's that story again. Here he's walking away. Said, really? You drive a car? Really? And just looked at me like, how? I never thought that you drove. And you're stuck in traffic. Didn't dawn on me. I think of you as a teacher, not as a commuter. Oh, no, yeah. I got to go to the light just like everybody else. So again, what am I? Am I a teacher or am I a commuter? I'm both, right? It all depends on what experiment to illustrate this. And this is a good experiment that illustrates the wave nature of light. And let's just keep going with this logic. Hopefully there'll be enough time to at least go through the logic, and we're going to run probably short on the numbers. But let me go to the next little slide here. Okay? I'll go to this kind of little animation. This is just kind of showing the intensity on the screen, so nothing new here other than, see how down the middle it's bright? Then as you move from the middle, it gets dark. Then it gets bright, dark, bright, dark, bright, dark. And again, the reason for that is because as you go up or down the screen, the distance from one opening to the other is different. And when they differ by a half, you're going to get destructive. When they differ by 1, you get constructive. When they differ by a half, you get 1 and a half, you get destructive. When they differ by 2, you get constructive. Yeah.
Shouldn't there be just as much light as there is like dark? I mean, should they be proportional, or is it just an illusion that it looks like there's more bright?
Oh, yeah, it's more of an illusion, because the truth is there's only one spot on the screen that is exactly constructive. And then over here, another point that's exactly destructive. And so the stuff in between is less constructive, less constructive, less constructive, less constructive, then completely destructive. But you can still see it. Okay, so these are points on the screen. The brightest point in the center of this dot is really the point I'm getting at. And then as you get away from that center point, you still see it with your eyes because you don't have complete destructive. And so that's why the bright ones will look wider, because you can see down until the intensity goes to 0. Or below some level and you can't see it. Now let me keep going in the few minutes we have left in this animation, because I'll start here with just some terminology. Here's how we'll label them. All right, so down the center, guess what we'll call it? Well, the central maximum. Maximum because this is where we get very bright light. We get constructive interference. It's in the center because it's, the way kind of where we start is the waves will be the same number of waves. In this case, it's 8 million from each path. They add up constructively. As you move away, you will hit a minimum in each direction, and then you will hit a maximum. We're going to label those. The first one away is a 1. The first one away is also a 1, but we'll give a negative in one direction and positive in the other direction. So this is positive and negative 1, positive and negative 2, positive and negative 3. So each of these maximums are numbered by this letter, or by this symbol M. And we'll use that in our equations, but probably not today there. But that's what we mean by the M. Now, here is where I think the animation does its best job here. This, of course, is a drawing of all these waves coming in. Now, obviously, there's not 8 million here, but there is a lot, and that's to illustrate that there is a lot. And look what happens when we take the magnifying glass and we focus right at the center. Right here, where the light hits the edge, see how the two beams come together, crests line up with crests, and troughs line up with troughs. You're going to get constructive interference, and at that point you're going to get the light very bright. And so that's the center point. As you move up the screen and we keep the magnifying glass, you will hopefully now see that the number of waves to here is slightly more than the number here. In fact, it's slightly more by a half a wavelength. And if you look with a magnifying glass on it, you will see that this one comes in and is hitting with a, I'll call it a crest, but this one is hitting with a trough. And what happens when a crest and a trough meet? Destructive. So you're beginning to understand how this can be explained with waves. This is our proof that this is an experiment showing that light is behaving as a wave. This can be explained in terms of waves. Let's go up the screen a little bit more. Let's go to the first bright one, m equal to 1. The reason we call it m equal to 1 is the bottom one is one wavelength longer than the top one. And the magnifying glass, I think, shows it really well that, again, the two crests and the two troughs line up, even though this has one more wavelength than that one. And as we continue to go up, we will see the same thing occur here at what we would call 1.5 m. That this one is 1.5 wavelengths further than that one. And as you look again at your magnifying glass, you will see that the crest lines up with a trough and you get destructive interference. I think it does it one more time. This is what we'd call the second maximum. The second maximum. This is where this bottom one is twice or has two more wavelengths than that one. And they line up. And so, here's the third minimum. So we are 2.5 wavelengths different. Here is the third maximum. So that bottom one is 3 wavelengths longer than the top one. Now, to do the math, let's put our magnifying glass down here. Because as you look at this colored triangle, I would say that the number of wavelengths here and the number of wavelengths here is the same. And that's why we get constructive. It doesn't matter if it's 8 million or 20 million or only 3 million. Because of the same number, you're going to get constructive interference. So regardless of the wavelength, you get constructive interference. But now, as we look at the first minimum, and we take the magnifying glass and we zoom in a little bit closer right here, as we tilt this triangle, this is what the author's trying to say right there. This bottom one is right there, a half a wavelength further. And that's why you get your destructive interference. If I go a little bit further up the screen and I analyze it up here at the screen and put my magnifying glass back here, the reason we get constructive here is because that is now 1 full wavelength further than the one above it. Yeah.
Why does the light change direction when it goes through that hole?
You mean why does it spread out and diffract? With the narrow opening? That's the part I said I'm going to show you and not explain until we understand this better. And when we understand this better, then I can explain that better. Yeah, I know it's kind of a weird thing. We're using it to do something else that we're going to use to explain it. But it's really not a circular reasoning, as much as it may seem. But you can see now this would be 1.5 wavelengths. This would be 2 wavelengths. And so again, notice I'm focusing on that extra distance right there. Now we can do some math here real quick. If we call D the distance between the two openings, little d, I should point out. Huh? From the, let's just say center to center of the holes. Because we really haven't given any size to our holes. We're just going to say they're really, really small so that the light spreads out, which means they have to be almost infinitesimally small. So at this point, we're really saying those holes don't have any size. And I should say slits. The slits don't have any width. But if you want to give them some width, which we will, it's real soon, then let's just say it's the center of the slit to the center of the slit. Okay? Well, I think we got one more animation. This is what, 2.5 wavelengths. Hopefully you can see it there. But here's where the math begins. Nope, there's 3. Now let's put in some dimensions here. Let's do our first equation and we'll call it quits for this chapter for today here. But look closely at this geometry. If you look at the triangle where the magnifying glass has been focused on, which Don has designed to turn red in color, and you call this part where we've been putting our magnifying glass delta, representing the path difference, how much further does this second one travel compared to the first? In other words, this rest of the distance I don't care about. The rest of that distance is all the way to the screen. And it can be 1 meter or 1,000 meters, doesn't matter. What matters is the difference between them. And the difference between them all occurs down here. And so as you look at this red triangle, as we have tilted up, if we call D, L, the length to the screen, and then D, the hypotenuse here, then can you see how this red triangle and that red triangle are similar? And so Don writes it there as delta is to little d. And so the opposite of sine is to the hypotenuse, as the opposite, y, is to d. And of course, using some trigonometry, isn't that the definition of the sine of the angle? Sine of this angle. So in other words, as I look at the screen, if I call straight down 0, and I go a little bit to my left or right, let's say I go 3 degrees, then the sine of 3 degrees would be path difference over the slit size. Here's the point in all that, and then we'll have to call it stops for today. There's sine theta. But if I take this first one and this one, I will have delta equals to d sine theta. And when do I get bright spots? And when do I get dim spots? Well, I get bright spots when this path difference is an integer number of wavelengths. Wasn't that our argument here? Wasn't that the whole point of putting the magnifying glass down here? When this extra path length, when this delta was either 0 wavelengths or 1 wavelength or 2 wavelengths, dot, dot, dot. So now you can see why we label them with an integer, right? That's where that m came from. M equal 1, m equal 2, m equal 3. So when d sine theta equals to m lambda, that is where you're going to get bright spots. Where are you going to get dim spots? Halfway in between, m plus a half. So when we have 1 half a wavelength, 1.5, 2.5, 3.5, 4.5. And so we have one equation, d sine theta equals m lambda. This is what we use to find the bright spots, constructive interference. D sine theta equaling m plus a half is where we get destructive interference. Well, we're out of time, so we'll call that quits there, but hopefully you see the